Now, I want to explain again the greedy strategy. The choice that seems best at the moment is the one to go for. This is the whole idea of greedy strategy. Instead of solving all possible options and choosing the best one, as we do in dynamic programming, no. Intuitively choose the option that looks the best at the current time in the hope that it will eventually give you the optimal solution. Okay. So what did we do for this problem in summary? First, we determine the optimal substructure. We then develop a recursive solution. Show that if we make a greedy choice, then only one subproblem remains. Okay, if we make a greedy choice, only one subproblem remains. And then prove that that greedy choice is safe using the cut and paste strategy that we have been using. Finally, we develop the recursive greedy algorithm and convert it to an iterative algorithm. So these are the steps we followed. However, we actually don't have to follow all those 6 steps. So at first, it looked like dynamic programming. In activity selection problem, we started out by defining subproblems Sij, where both I and j varied, but then found that making the greedy choice allows us to restrict the subproblem to just one. Now, instead of doing this, actually, we could have just gone straight away to the greedy approach. Okay? In our first attempt of finding subproblem, we should just use the greedy choice. Use the notation Sk rather than Sij. We could then prove that the greedy choice, Am, combined with the optimal solution to the remaining compatible activities, Sm, will give an optimal solution to Sk. Okay? So typically, if you are following greedy strategy, these are the main thing you have to do. You don't have to follow all those 6 steps that we have followed in this example. We did them just to show you the relationship between greedy and dynamic programming. Typically, this is what you have to do. Cast your optimization problem as one in which we make a choice, one choice, and then we are left with one subproblem to solve. Don't try to don't try to have 2 subproblems, because if you do that, you are more or less doing it like dynamic programming. No, think about what greedy choice can you make, so that when you do that choice, then there will be only one subproblem to solve. This is the starting point. Okay? Of course, you need to prove that there is always an optimal solution that makes a greedy choice, so that the greedy choice is always safe. Yeah, the greedy choice you make in step 1 here, you have to prove that it is safe. Okay? And then demonstrate optimal substructure by showing that having made the greedy choice, combining an optimal solution to the remaining subproblem with the greedy choice will give an optimal solution to the original problem. Okay? So those are basically the steps you need to do. Once you are able to do that, then go ahead and define your recursive solution and then convert it into iterative version. Okay, this is how to do it basically. You don't start by casting the problem as one that has 2 or more subproblems. No, only one subproblem. After making a greedy choice, there is one subproblem. Okay, try to prove that the greedy choice is safe, and that the subproblem will actually give you an optimal substructure. These are important. Okay, so here are the elements of greedy strategy once again. Of course, there is no general way to tell whether a greedy algorithm is optimal or not, but two key ingredients are important. One is that there is a clear greedy choice property, okay, and the second is that there is optimal substructure. If you can have these two, then most likely you will be able to solve the problem using the greedy strategy. Okay, so this is similar to dynamic programming. The optimal substructure is there, but in the case of dynamic programming, the next criteria to look for was that the subproblem are overlapping. So overlapping subproblem was the second important issue in the case of dynamic programming. Here, no. The issue is, can we make a safe greedy choice? So if there is an optimal substructure and there is a greedy choice that can be proven to be safe, then you can solve the problem with greedy strategy. Okay, so just to emphasize again on the greedy choice property, is that can we assemble a globally optimal solution by making locally optimal choices? Okay, if you can have that, then you have the greedy property. This is in contrast with dynamic programming, which make a choice at each step, but that choice depends on knowing optimal solution to the subproblems. And therefore, in dynamic programming, you have to solve the subproblem first. Okay, and you're going to solve them in the bottom-up approach. In greedy, on the other hand, we just make a greedy choice and make the choice before solving the subproblem. Okay, so the reverse here, we have to solve the subproblem before we can make the choice. No, here we just make the choice without solving the subproblems, and then we solve the subproblem top down, not bottom up, like dynamic programming. This is basically the comparison between the two the two design techniques. Typically, show the greedy choice property exists, or showing the greedy choice property exists is similar to what we did in a similar way to what we did for the activity selection problem. Look at an optimal solution. If it includes a greedy choice, then we are done. Otherwise, modify the optimal solution to include the greedy choice, okay, yielding another solution that is just as optimal. Okay, so this is the way to show that the greedy choice property exists. Okay, we can get efficiency gains from greedy choice property. Pre-process input to put it into greedy order. As we said in the activity selection, we sort the activities based on the finishing time. So typically you can gain efficiency in making your greedy choice if you do some pre-processing. Okay, if you don't, you may have to do extra effort in the algorithm itself. Okay, or it says here if the data is dynamic, so we cannot do pre-process because the data is going to be dynamic, then as I said earlier, just use a priority queue. So you will be putting your data in a priority queue, and then you will pick in the next activity. You will be making your next greedy choice by choosing the next priority element, basically. Okay. So that is basically the idea of greedy algorithm. We're now going to try and compare between greedy and dynamic programming by looking at an interesting example. So it says, because both the greedy and dynamic programming strategies exploit the optimal substructure, one might be tempted to generate a DP solution when in fact a greedy solution will suffice. Conversely, one might mistakenly think that a greedy solution will work, while in fact you have to do it using DP. Okay, we're going to take an example called knapsack problem to show, to emphasize these 2 points. The knapsack problem is a good example showing when each strategy applies. So this is a knapsack problem. It's an interesting problem actually. It says, assuming that we have a thief that is trying to rob a store. The store has n items, or the thief finds n items in the store. Okay, and the items are such that they have different values. Okay, so the ice item is worth VI reals. This is the value of the ice item, VI reals, or dollars if you want, and it weighs WI pounds. Now the thief has a restriction. He can only carry W pounds. If he fills his sack more than W weight, he cannot take it out because it would be too much weight. Okay, so there's restriction. The thief can carry at most W pounds. Okay. Another assumption is that VI, the value for the item I, WI, the weight for item I, and W, the total weight that the thief can carry, they are all integers. Okay, so the question is, which items should the thief take to obtain the maximum amount of money? Okay, so there are 2 versions of the knapsack problem. There is what is called 0-1 knapsack. In the 0-1 knapsack problem, each item is taken only one time or is not taken at all. And if you take it, you have to take it as a whole. There is no fraction allowed. Okay. On the other hand, the fractional knapsack version, so the other version is called fractional knapsack. Here, fractions of items can be taken. Okay. Now we're going to try and solve both of them and see whether we can apply greedy approach to both of them. One of them can be solved with greedy and the other cannot. Now the first thing to note is that both of them exhibit the optimal substructure property. Why? For the 0-1 knapsack, if item J is removed from an optimal packaging, so suppose the thief has chosen his optimal solution and it includes an item J. Now suppose you remove that item J. Can we say what is remaining is also optimal for the remaining weight that remains in his sack? Okay, so the remaining packaging is also an optimal packaging with a weight of at most W, which is the total weight of the sack that he can carry, minus WJ, the weight of the item J that has been removed. Okay, you will see that it is actually optimal. Similarly, for the fractional knapsack, if W pounds of item J is removed, okay, so not all of item J, only W pounds of it is removed from an optimal packaging, then the remaining packaging is also going to be an optimal packaging, and its weight is going to be at most the total weight minus W that can be taken from n-1 items plus wj minus w, because he took out only w. So if you add this, again you will see that there is no better packaging that will give you an optimal solution considering n minus 1 items. So actually both of them will exhibit the optimal substructure property. Now let's look at the fractional knapsack and see how we can solve it using greedy approach. So this can be solved by the greedy strategy, because all you have to do is compute the value per pound for each of the item. The item that has the most value based on the weight is the most valuable item. Okay, so the greedy choice will say, okay, take that one first before you consider others, right? Take as much as you can of that, rather, because here fractions are allowed. Okay, so obeying a greedy strategy, take as much as possible of the item with the greatest value per pound. Okay, if the supply of that item is exhausted and there is still more room in his sack, then the thief can take as much as possible of the item with the next value per pound, and he will continue doing this until he fills his sack or until the items are exhausted. This is the greedy algorithm for this. This is the algorithm. So fractional knapsack, take 3 input, V, W, and W. Okay, initialize load to 0 and I to 1. So we are saying while the load, the total load that he is packaging, is less than the total weight he can carry, W is the total weight he can carry, and I is less than N, we have not exhausted all the items, you check if the weight WI is less than or equal to, so the weight of item I, if it is less than the total weight he can carry minus the load so far, then take all of item I. Okay, if you can take all of it, take it. Otherwise, you take as much of it as you can. So take W minus load divided by WI of item I and add what was taken to load. Increment your I to 1 to consider the next item. Okay, obviously this algorithm will be either big O of n or n log n, depending on whether the elements are sorted according to their values or not. Okay, so if sorted, A or big O of n. If not sorted, n log n. This will be the running time, because the loop here, of course, will run at most just n times. But the problem is, how do you choose the next item? If it is sorted, nothing else is needed. But if it is not sorted, it has to be sorted, and that will take n log n. Okay, so that is the fractional knapsack. I will show you graphically this problem applied to some items. But before that, let's look at the 0-1 knapsack. Now 0-1 knapsack, unfortunately, is much harder, and in fact you cannot apply greedy strategy to it. And we're going to show you this with a counter example. Here we must compare the solution to the sub-problems in which the item is included with the solution to the sub-problem in which the item is excluded before we can actually make a choice. We cannot just make a greedy choice in the 0-1 knapsack, as I will show you in the next step. So in this case, actually, we have to apply dynamic programming. Must apply dynamic programming to solve the 0-1 knapsack, although you can solve it for the fractional knapsack using greedy. Okay, this is our counter example. Okay, so greedy doesn't work for 0-1 knapsack problem because we might get empty space which will lower the average value per pound of the item. Let us take this example. So suppose we have these three items. Item 1 of weight 10 pounds, and it cost $60, or its value is $60. Item 2, the weight is 20 pounds and the value is $100. And similarly, item 3 is weighing 30 pounds and its weight is, its value is $120. The thief is allowed or can take as much as 50 pounds. So capital W is 50. This is the weight the thief can carry, 50. Now, if you want to solve this problem using greedy strategy, the first thing you need to do is to compute the value per weight. And this table is showing you the value per weight. Item 1, the value is 60 and it weighs only 10. So the value per weight is actually 6. Whereas item 2, the value per weight is the value 100 divided by 20, which is 5. And the last one, item 3, its value is 4, 120 divided by 30. So the more valuable item actually is item 1. Okay? Now, if you are going to solve this problem, if you're going to solve the 0-1 knapsack problem, based on this, the greedy choice says go with the one that is most valuable. Okay, so we're going to take item 1 because it is the most valuable. Okay, so we're going to take item 1. So he will have already occupied 10 out of his 50 allowance in his sack. Next valuable is item 2 because its value per weight is 5. So he will take item 2. Okay, so he will take item 1 and 2, and the value so far is 60 plus 100. Okay, but now he's going to be in trouble because he has already occupied 10 plus 20 pounds out of his allowance of 50. That means he cannot take item 3. Because remember, fractions are not allowed in the 0-1 knapsack. So if he has already occupied 30, 30 plus 30 will be 60. This will be above the maximum he can take. So if he's following the greedy choice, he will have taken only item 1 and item 2. And the value he will get is actually only $160. Okay. However, if he had, and of course by doing that, he will have been left with a capacity of 20 pounds, which he cannot use. He cannot utilize that remaining capacity. But the optimal solution actually is to take item 2 and 3. Okay, item 2 is 20. Item 3 is, the weight is 20 pounds. Item 3, the weight is 30 pounds. So he will fill his entire 50 pound weight sack, and the value he will get is 100 plus 120, which is 220. Obviously 220 is much better for him than getting only 160. So this is the optimal solution, and he will have no leftover capacity. Okay, this diagram is showing the possible options actually. One option is to take which is the optimal, take the 20, the item 2 and item 3. So he will have 220. The other option is which he did was to take item 1 and item 2 based on the greedy choice here. Greedy choice means go with the most valuable item first. So he went with item 1 and the next valuable item is item 2. So he ended up with only 160 pounds. Okay, the other choice will have been item 1 and item 3. Even that is better than his greedy choice because he will have 60 plus 120, which is 180. Okay, so this is an example showing you that greedy choice doesn't always work. He was greedy by saying he will go with the most valuable item. Okay, but it turns out his overall optimal solution was not really optimal. Okay, the final picture here is showing you the solution to the fractional part, showing you that if we follow greedy approach here, yes, we will still have optimal solution. Okay, according to the greedy strategy here, take the most valuable item. So he took 10 pounds of item 1. Basically, he took item 1. Okay, so the value was 60. He also took item 2. But in fractional knapsack, fraction are allowed. So although he cannot take all of item 3, he can take 20 out of it with a value of 80. So his overall value is 240, which is good. Okay, so fractional part can be solved with greedy approach, but 0-1 knapsack cannot. This is an example showing you that it is not always that the greedy choice will work. Okay, the choice looks good, but it turns out to be it is not safe, unfortunately. In this case, only the DP can solve it. So that is the end of the lecture. There are 2 exercises left, given to us to do here. First one says, give a dynamic programming algorithm for the activity selection problem based on the recurrence that we obtain in in equation 16.2 of the book. Okay. We have the same equation actually in the slide if you look at it, where we got the Cij equal to something. So look at that equation, and instead of solving with greedy approach, continue with the dynamic programming approach that we started and solve the problem. In other words, have your algorithm compute the sizes Cij as defined in that equation, and also produce the maximum size subset of mutually compatible activities. Assume that the inputs have been sorted as in equation 16.1. Okay. So having solved it with dynamic programming, now compare the running time of your solution to the running time of the greedy activity selector. The solution we solve using dynamic programming. And the second and last question is, suppose that instead of always selecting the first activity to finish, rather we select the last activity to start that is compatible with all previously selected activities. Okay, so instead of selecting the first activity to finish, no, select the last activity to start that is compatible with all previously selected activities. Describe how this approach is actually a greedy algorithm and prove that it yields an optimal solution. All right, those are the 2 exercises. In the next lecture, we will take another more interesting example which also applies greedy algorithm. It is called Huffman coding algorithm. Thank you very much.